Okay, so in today's lecture, we're going to cover section 5.4. This is exponential functions. Okay, and this is both integration and differentiation. So, two lectures back, we introduced the natural log function. And then after studying the natural log, we learned about inverse functions, right? Well, the exponential function is going to be defined as the inverse of the natural log. And we know that, so maybe you can recall, increasing functions are invertible, or yeah, are invertible. Okay. Increasing functions have an inverse, and the natural log function is increasing. So it has an inverse. Okay. All right, so let's look at that definition now. Okay. The inverse function of the natural logarithmic function or natural log. So the inverse function of that thing is called the natural exponential function. Okay. And it's denoted by, so if that's your function f, f inverse of x is equal to e power x. So that's exponential e that we introduced several lectures ago. So just recall e is the positive real number with natural log of e equal to 1. And that's how we defined exponential e. And now that we know about inverses, we define the inverse of the natural log as this natural exponential as e to the power x. Okay. So in particular, the important equation to remember, or not equation, the important biconditional statement is that y is equal e to the x if and only if x is equal to natural log of y. Okay, so this is the important equivalence here. Okay. And again, this inverse, so natural exponential function. That is the inverse function of the natural log. So it's important to note that if you compose natural log with its inverse, you get back x. And if you compose the natural exponential with your natural log, you get back x. And that's just by these functions being inverses of each other. Okay. What's more is that we know that the natural log function looks something like this. And when we were studying inverses, we saw that the inverse function's graph will be somewhat reflected over the line y equals x. So this would be exponential e. Okay. All right, so maybe before getting to the calculus of the exponential function, i.e. the derivatives and the integrals, maybe we can review some algebra involving these functions. So maybe like review for 2 problems, I don't know, what did I have here? So for example, solve the equation 7 equals e to the x plus 1 for x. And then the other example would be solve natural log of 2x minus 3 is equal to 5. Okay, so this is something that you could learn to do in a pre-cal class or college algebra class. So here we have 7 is equal to e to the power x plus 1. So then we could say we can take the natural log on both sides. And then we know that exponents become coefficients in the natural logarithm. And then we know that natural log of e is 1. And then we subtract 1 on both sides and we get our solution. Okay, that's just review of algebra, right? So here, I suppose we can do the same trick, right? We can raise both sides of this equation to base e. So e raised to the power natural log of 2x minus 3 is equal to e raised to the power of 5. And by this property here, because these are inverses of each other, we get that 2 times x minus 3 is equal to e to the power of 5. 2x is equal to e to the power of 5 plus 3. And then finally, x is equal to that divided by 2. So it's just reviewing the basic techniques of solving exponential equations and natural logarithmic equations. Okay, so now back to calculus. And again, all of you should be familiar with E, with natural log. That's why we're kind of moving quickly through their definitions, and he didn't even talk about their properties like e to the power 0. That's that intercept, things like that. The main thing we want to get to is the calculus of these things. Okay, so, the theorem. I don't know the number of it in the textbook, but it is a theorem. It says, let u be a differentiable function of x okay. And there's 2 parts to this. So, one, the derivative with respect to x, the natural exponential function, it's just itself. And then part 2, derivative with respect to x of e to the power u is going to be eu times du dx. And that's just an application of the chain rule. Okay. So why would this be the case? Why, if we don't have to prove that one, we just have to kind of argue to ourselves why that's true, and then this is just the chain rule. What do I have here? Let's see. So suppose take the derivative with respect to x of that. Okay. So what does this become? Well, because these are inverses of each other, this inside is just x, right? Okay, so this is just equal to 1, right? These are inverses, so this becomes x, and the derivative of x is just 1, right? Okay, so why does this help us prove that? Well, this is equal to, so this is using properties of inverses to get from there to there. Now I'm just going to suppose that I didn't know they were inverses, and I'm just going to apply what I know about taking the derivative of the natural log, right? So this is 1 over the inside times the derivative of the inside, right? So this is 1 over the inside times the derivative of the inside, right? But this is equal to that, equal to that, equal to that. So altogether, this is equal to 1. So then we multiply both sides by e to the power x. We get that d dx is equal to power x. So it's kind of a sloppy proof for part 1 of that theorem. And then the second part is just applying the chain rule. Okay, so these are the major differentiation bits to this section. So might as well do some examples now. So take part A, e to the derivative of e to the power 2x minus 1, and then b, the derivative of x squared times e to the power x. simple examples here. So, okay, so what does this say? So in both cases, we have u up top as a function of x. So here, this is just going to be e to the power u times the derivative of that with respect to x. So e dx of 2x minus 1. So altogether, this becomes 2 times e to the power 2x minus 1. That's it. Okay, here, this is more or less just the product rule for derivatives. So it's a derivative of the first times the second plus derivative of the second times the first. So this would be 2x times e to the power x plus e to the power x times x squared. The derivative of e to the power x is just e to the power x. And that's it. Maybe there's a better example problem I can give you. Oh, I got one. So as you probably know from my first lecture, first day, when it comes to calculus, I'm often concerned with maximum, minimum optimization problems. So let's look at one of those. Example, find the relative extrema for the function f of x equals to x times e to the power x. Okay, so in order to do this, there's a few steps, right? So to find the relative extrema, we need to find the places where the derivative is equal to 0 or it doesn't exist. So f prime of x. So this is again the product rule, derivative of that times that plus that times the derivative of that. So we get e x times e to the power well there plus x times e to the power x. And just to make life a little bit easier, I'm going to factor that out. That. And the only places where this is equal to 0, so the only places where this is equal to 0 is when x is equal to -1. So, and it exists everywhere. So the only critical number is x equals to -1. So f evaluated at that -1 is a relative extrema, whatever that value is. So f -1 equals to -1 over e is a relative extrema. Okay. And the question didn't ask you to determine if it was a relative minimum or relative maximum. How would you do that? Any suggestions? To determine if it was a max or min, you would take the second derivative. Okay. Or you could look to the left and the right of x equals -1 and look at the first derivative. If the first derivative is increasing and then it's decreasing after that point, what would that tell you? Okay, so again, maybe go in the textbook and review finding relative extrema and just review those things so that I will probably ask questions about them in the future. Okay, so these are just examples. I think it's fairly straightforward. You know the chain rule well by now. You know the theorem. Derivative of e to the power u is e to the power u times du dx. That's it. So I think we can move to integrals. Okay. So is that u be a differentiable function of x and again there's two parts to this, so these are both indefinite integrals. So indefinite integral of this, well, if you understand how integrals and derivatives are inverses of each other, you would see that this is e to the x plus c. Right? Because the derivative of e to the x is e to the x, and this is the antiderivative. So if we want to know the antiderivative of e to the x, well, that's where we came from. Again, plus some constant c. Okay. And then, of course, e to the u du is equal to e to the u plus c. And this e to the u du, if you can just take a natural exponential function and write it in terms of u, then you can integrate it just like normal. Okay. Okay. So let's look at some examples. A indefinite integral e to the 3x plus 1 dx, and then b 5x e to the minus x squared dx. Okay, so here we would just need to identify our u in this case. So it looks like u would be 3x plus 1. So that means that du is equal to 3 dx. Okay. In other words, 1/3 of du is equal to dx. So then this would be 1/3 of e to the power u du. I just divide both sides here by 3, take the 3 out in front of the integrand, and then using our theorem here, this is just 1/3 of e to the power u plus c, but what is u? It's 3x plus 1. Okay, so what about here? This looks like my candidate for u up here. So if u is equal to negative x squared, then du is equal to negative 2x dx. So over here, I see a 5 and x, but I do see x dx right here, and I see x dx right there. So here I'm going to say that negative du over 2 is equal to x times dx. So if I take that 5 out, and then if I take the negative 1/2 of du out, I get e to the power u du. Right? In case you don't see it, just in case you don't see it, I took the 5 out, and then I had e to the negative x squared times x dx right there. And then in place of x dx, I wrote negative 1/2 du. And then I took the negative 1/2 out, and I'm just left with what I need. So then altogether, this is negative 5/2 of e to the power negative x squared. Let's see. Don't forget your constant of integration. Okay. Now let's do maybe a definite integral example. Okay. Say 0 to 1 e x all over 1 plus e power x dx. Okay, so immediately I see that if that's my u in the denominator, then my du is in the numerator. That's good. Whenever you see that, then we can use the natural log. So if u is equal to 1 plus e to the power x, then du is equal to e to the power x times dx. So there's u and there's du. So this is 1 over u du. And now we need to change our limits of integration. So when x is equal to 0, u is going to be 2. And then when x is equal to 1, u is going to be 1 plus e. Right? And now we know how to take this integral here. So this will be natural log absolute value of u evaluated from 2 to 1 plus e. So then this will just be it's positive. I can drop the absolute values if I want to. Whatever that number ends up becoming. This will be some numerical value, but that'll be it. Okay. Okay. So that will conclude our lecture on the natural exponential function. And from this section, the suggested homework will be 3 through 13, 33 through 47, and 97 through 115. Okay, so I'll go ahead and stop the recording here.